Welcome back. In this video, you will learn how to use integration by parts to solve integrals. Let's get to it. Alright, and so integration by parts is an integration technique that can be used to integrate functions that we previously could not have integrated. So if you take a look at these two integrals here, we have the integral of x times e to the power of x and the integral of x times sine x. We currently don't know any integration techniques that will allow us to successfully integrate either of these integrals. And you'll notice that in each of these integrals, we have a product of two functions, right? We have x times e to the power of x and x times sine x. Previously, up until this point, if we had a product of two functions within our integral, we were able to solve them using u substitution. However, in this case, that's not going to work. If we try to use u substitution and set one of the functions within our integrand equal to u, the derivative of that function could not also be found within the integral, and so u substitution is going to fail. It's not going to work. And so in order to solve integrals that feature a product of two functions that can't be integrated with u substitution, we need integration by parts. And so integration by parts is going to be very helpful in integrating products of different types of functions. And so here I have the 5 most common types of functions that you will encounter in integrals that need to be solved with integration by parts. You might see an algebraic function or some type of polynomial such as x squared. You might see trig functions such as sine x. You could also see an exponential function such as e to the power of x. And then you could also see inverse trig functions, such as arcsine of x. And then you might also encounter logarithms, such as the natural log of x. And so when you see a product of two of these different types of functions in an integral, and you know u substitution isn't going to work, then integration by parts is going to be your friend. Alright, and so before we look at some examples, we need to talk about what the integration by parts formula is and where it comes from. Okay, so the integration by parts technique is actually based on the formula for the product rule for derivatives. And so if you remember the product rule for derivatives, we know that the derivative of two functions multiplied together, f of x and g of x, is equal to f of x times the derivative of g of x plus g of x times the derivative of f of x. And so essentially what we're going to do here is undo the product rule by integrating both sides of the equation. And then with a little manipulation, we will have our formula for integration by parts. And so if we do that, if we integrate both sides of the equation, we will have the integral of the derivative with respect to x of f of x times g of x, and that will be equal to the integral of f of x times g prime of x. And then since we're taking the integral of that product, I'm going to add dx onto the end, and that will be added to the integral of g of x times f prime of x, and then I'll also write dx for that integral. Okay, so we just integrated each part of this equation. And so now the integral is going to reverse the differentiation process, and so the integral of the derivative of the product of these two functions will just be equal to these two functions. So we will have f of x times g of x, and that will be equal to these two integrals. And so I'll rewrite those real quickly. And now what we're going to do is subtract this integral from both sides of the equation. And so if we do that, we will have f of x times g of x, and then we will subtract this integral. So we'll have the integral of g of x times f prime of x times dx, and that will be equal to this integral, which is the integral of f of x times g prime of x times dx. All right, and so this equation right here is the integration by parts formula, but it does look a little bit different than how it's typically presented, and so let's rewrite this into a more simplified form that is a little bit easier to understand. And so if I clean up my work here, what we're going to do here is we're going to let u be equal to f of x, and then we're going to let v be equal to g of x. And so what that means is that du dx, or the derivative of u with respect to x, will be equal to f prime of x. And so if you multiply both sides by dx, du will be equal to f prime of x times dx. And then if we take the derivative of v with respect to x, we'll have dv dx is equal to g prime of x, and multiplying both sides by dx here will give us that dv is equal to g prime of x times dx. And now we can use u, v, du, and dv to rewrite this expression into a simpler form, which will give us the typical formula that is used for integration by parts. And so let's replace f of x with u and g of x with v. So if we rewrite this equation down here, we will have u times v, and then we will subtract the integral of g of x, which is v, so we will have v, and then that is multiplied by f prime of x dx. And we know from right here that f prime of x dx is equal to du, and so we will have v times du, and that will be equal to the integral of f of x, which is u. So we will have u, and then that's multiplied by g prime of x times dx, which we know is equal to dv. And so we will rewrite that as dv. And so this right here is the typical formula you will see for integration by parts. The integral of u times dv is equal to u times v minus the integral of v times du. All right, and so this is the formula for integration by parts that we are going to use to solve integrals that we wouldn't have been able to solve otherwise via any other method. What we're going to end up doing is setting a part of our integral equal to u, and then setting another part of the integral equal to dv, and then use those different parts of the integral to set up the other half of this formula. And what that's going to do is give us some term minus another integral that should be easier to solve so that we can solve our integral. And so that might sound a little complicated, but it's actually not as complex as it sounds. And so let's take a look at our first example problem where we will use this formula. All right, so here's our first example. This is actually one of the integrals I had at the beginning of the lesson that I said we didn't know how to solve, but now we're going to solve it using this integration by parts formula. And what we have is the integral of x times e to the power of x times dx. Now what you want to do to solve an integral using integration by parts is set part of this integral equal to u and set the other part equal to dv. And so determining what to set equal to u and dv is arguably the hardest part of integration by parts. But once you understand why you want to set something equal to u versus setting something equal to dv, integration by parts becomes a whole lot easier. And so I want to try to make it very clear why you want to set something equal to u versus dv. All right, so we're looking to rewrite this integral, which is currently in this form, the integral of u times dv, and we want to rewrite it to be u times v minus the integral of v times du. But now notice, we don't have v or du, we're just going to have u and dv in our integral. And so in order to get v and du, we are going to have to manipulate u and dv. Specifically, to get du, similar to u substitution, we are going to need to take the derivative of whatever we set equal to u. And then in order to get v, we are going to need to integrate whatever we set equal to dv. And so when determining what to set equal to u and dv, you want to ask yourself, which of the two functions in my integral, if I set equal to u, will get simpler when I take its derivative? Because that derivative, du, is going to appear in the new integral that we will write when using integration by parts. And so we want that integral to be simpler or easier to solve. And so if we take a look at each of the parts in our integral, if you take the derivative of x, that's just going to be equal to 1. But if you take the derivative of e to the power of x, it's still e to the power of x, right? The derivative of the exponential function, e to the power of x, is itself. So it doesn't get any simpler, it just stays the same. But on the other hand, x became 1. And so that's going to be our choice for u. Now we're going to look at an example later on where there is an exception to that rule, but for most cases, that will help you determine what to set equal to u. And so let's do that for this integral. We'll set u equal to x, which means that dv is going to be e to the power of x times dx. And so we'll have dv is equal to e to the power of x times dx. And so now what we want to do is take the derivative of u and integrate dv. And that is going to give us du and v. So let's start by taking the derivative of u. We'll have du dx is equal to 1, right? The derivative of x is just 1. And then if we multiply both sides by dx, we will have that du is equal to dx. All right, so we have du. Now let's find v by integrating dv. And so we'll have the integral of dv is equal to the integral of e to the power of x times dx. And the integral of dv is just going to give us v, which will be equal to the integral of e to the power of x, which is just itself, right? The integral of e to the power of x is just e to the power of x, and so we will have e to the power of x is equal to v. All right, and so now we can use everything that we have here to rewrite this integral in this form. So we will have that this integral is equal to u times v. So we have u is equal to x, and v is equal to e to the power of x. So we will have x times e to the power of x minus the integral of v times du. And so v, once again, is e to the power of x. So we'll have e to the power of x, and that will be multiplied by du, which is just dx. And so I will write dx. Okay, and so what that did was it allowed us to rewrite this integral to be equal to a term that doesn't need to be integrated anymore, minus an integral that is easier to solve. We know how to integrate e to the power of x. It's just e to the power of x. And so this will be equal to x times e to the power of x minus e to the power of x. And then because we're working with an indefinite integral, you need to remember to add c. And so x times e to the power of x minus e to the power of x plus c is the answer to this integral. That is how you use integration by parts to solve an integral that we otherwise would not be able to solve. Okay, let's look at another example. All right, so here's our second example. This is the other integral that I showed you at the very beginning of this lesson, where I said we did not know how to integrate this, but now we can with integration by parts. And so we have the integral of x times sine x dx. And so if we're going to solve this integral using integration by parts, we need to determine what we're going to set equal to u and what we're going to set equal to dv. And so let's start with u. We want u to be a function that when you take its derivative, it gets simpler. And so in this case, we have x and sine x. If you take the derivative of x, x becomes 1, like we saw earlier. And if you take the derivative of sine x, it becomes cosine x. And so I wouldn't say that sine x becoming cosine x is any simpler. It just became another trig function. And so I believe it makes more sense to set u equal to x. And so let's do that. We will set x equal to u. So we'll have u is equal to x. And then we will set dv equal to sine x dx. So we will have dv is equal to sine x dx. And so now we will take the derivative of u and integrate dv. And so let's start by differentiating u. So we'll have du dx is equal to 1, which is the derivative of x. And then if we multiply both sides by dx, we will have that du is equal to dx. Okay, and so now if we integrate dv, we will have that the integral of dv is equal to the integral of sine x dx. Now the integral of dv will just be v, and that will be equal to the integral of sine x. Now the integral of sine x is negative cosine, and so v will be equal to negative cosine x. Okay, and so now let's use everything we found to rewrite this integral in this form. So we will have that the integral of x times sine x dx is equal to u times v. So we have x, which is u, and negative cosine x, which is v. So we will have x times negative cosine x, and then we will subtract the integral of v, which is still negative cosine x. So we'll have negative cosine x times du, which is dx. And so we will write dx. Okay, and so by the way, if you keep your work organized like I have over here, a little helpful trick for remembering what goes inside your integral, it's just going to be your two bottom lines multiplied together, right? So if you write your work the way I do, where you have u, you take the derivative, and then you have du, and then you have dv, the integral of dv, and then v and du, which are inside the integral, will be on the bottom of your work, and so you just multiply those together in your integral. Just a little tip, that's something that I like to do to keep my work organized and make sure that I put the correct values in my integral. But now let's simplify. X times negative cosine x will be negative x times cosine x. So this is equal to negative x times cosine x. And then we will subtract the integral of negative cosine x dx. But these two negatives will cancel out to become positive. So we will have plus the integral of cosine x dx. And the integral of cosine x is just sine x. And so we will have that this is equal to negative x times cosine x plus sine x, and then don't forget to add c at the end of your answer, and this is the solution to this integral by using integration by parts. Okay, so now before our next example, I want to show you something with regards to choosing u. Because up until this point, I have been telling you that when you choose u for integration by parts, that you want to set u equal to whatever function gets simpler when you take its derivative. And so while I find that to be very helpful, I understand that some people would rather have a set of guidelines than trust their own intuition. And so if you're looking for some kind of trick or a general guideline of what to set equal to u, this trick here should be helpful to you. When determining what to set equal to u, you want to remember the acronym Ly8, where the L stands for logarithms, the I stands for inverse trig functions, the A stands for algebraic functions or polynomials, the T stands for trig functions, and the E stands for exponential functions. Essentially what this is, it's a priority list. So when you're looking at the product of functions in your integral, and you see a logarithm times an algebraic expression, you should choose the logarithm to be equal to u because it's higher up in the list. So like I said, think of this as a priority list. If you have two of these types of functions multiplied together, whichever one comes first in the list, you probably want to set equal to u. Now this isn't a perfect list. It's not going to work perfectly for every single integral, but it is going to work a majority of the time. And also note that the last two here are interchangeable. If you have a trig function times an exponential function, it doesn't matter which one you set equal to u or dv. Your answer will still be correct. At that point, it just kind of comes down to preference. We put trig functions before exponential functions in this list so that the acronym can be pronounced. That's pretty much the only reason, so that we can say Ly8 instead of Ly8, right? It's a little bit easier to say Ly8 and remember that. Okay, and so if you're looking for a set of guidelines, this is for you, but I personally tend not to use this trick all that much. It all comes down to preference. All right, and so with that, let's look at another example. Okay, so here's our next example. We want to integrate x times the natural log of x times dx. Now, if you're using the guidelines that I just showed you, then you can see right away that we have an algebraic function, x, times a logarithmic function, the natural log of x. And so from that acronym, we know that we should set u equal to the natural log of x, and that will work just fine. But if we don't use the acronym, and you ask yourself the question, which of these two functions, if you set equal to u, gets simpler when you take its derivative, it's actually a little bit unclear, because if you take the derivative of x, you get 1, and the derivative of the natural log of x is 1 divided by x, and so both of them change, and it's hard to say which one is getting simpler. But notice that if you set the natural log of x times dx equal to dv, remember that you're going to have to integrate that, and we don't know a rule for integrating the natural log function. And so because of that, I'm going to lead towards setting u equal to the natural log of x, because it's a lot easier to take its derivative, and we know how to integrate x. That's pretty simple. And so I think we should set u equal to the natural log of x, which, like I said, you could have also determined from that list that I showed you earlier. Okay, and so we'll set u equal to the natural log of x, so we'll have u is equal to the natural log of x, and we will set dv equal to x times dx. And so dv is equal to x dx. Okay, and so let's take the derivative of u, and let's integrate dv. So du dx is equal to the derivative of the natural log of x, which is 1 divided by x, and then multiplying both sides by dx will give us that du is equal to 1 divided by x times dx. Now if we integrate dv, we'll have the integral of dv is equal to the integral of x times dx, and so we will have that v is equal to the integral of x. Now if we use the power rule of integration, we'll add 1 to the exponent and divide by that new exponent, so we'll have x squared divided by 2. Okay, and so now let's use what we have here to rewrite this integral into this expression. And so we'll have that this integral is equal to u times v, So we'll have the natural log of x times x squared divided by 2. So we'll have the natural log of x times x squared divided by 2. And then we will subtract the integral of v times du. And so v is equal to x squared divided by 2. So we'll have x squared divided by 2 times du, which is 1 divided by x dx. And so we'll multiply by 1 divided by x dx. Okay, and so let's simplify a little bit. If we pull this 1/2 to the outside here, this will be equal to 1/2 times the natural log of x times x squared. And then we will subtract this integral. And if I pull this 1/2 to the outside, we'll have 1/2 times the integral of x squared times 1 divided by x. Now this x will cancel out with one of these x's, and so we're just going to be left with x times dx in the integral. And so we'll have that this is equal to 1/2, and then I'm going to reorder the multiplication of these terms. It doesn't matter, I just like to write x squared first, so we'll have x squared times the natural log of x, and then subtract 1/2 times the integral of x, which again is x squared divided by 2, and then don't forget to add plus c. Okay, and so if I clean up my work here, we can simplify this answer, and we'll have that it's equal to 1/2 times x squared times the natural log of x minus x squared divided by 4 plus c. Okay, and so that is the solution to this integral by using integration by parts. All right, so here's our next example. We have the integral of the natural log of x times dx. And so if you remember from the previous example, I said we don't really know how to integrate the natural log of x. Well, I sort of lied because we can actually integrate it using integration by parts. And so what we're going to do is set the natural log equal to u, and then just set dx equal to dv, and we will be able to integrate the natural log using this integration by parts formula. And so we will have that u is equal to the natural log of x, and dv is equal to dx. All right, and so the natural log of x is u, and dx is dv. And so if we take the derivative of u, du dx will be equal to 1 divided by x, right? 1 divided by x is the derivative of the natural log function. And so multiplying both sides by dx will give us that du is equal to 1 divided by x times dx. Now if we integrate dv, we will also integrate dx, and so we'll have the integral of dv is equal to the integral of dx, and so we will have that v is equal to x, right? We're just integrating 1 essentially, and so the integral of 1 with respect to x is x. Okay, and so let's rewrite this integral using this expression. So we'll have u times v, which will be the natural log of x times x, and so this is equal to the natural log of x times x, and then we will subtract the integral of v, which is still x, times du, which is 1 divided by x times dx. So we will have times 1 divided by x dx. Now notice that this x will cancel out with this x, and so we're just going to have the integral of dx, or the integral of 1 dx. And so if we simplify, this is equal to x times the natural log of x. I just reordered the multiplication here. It just looks a little bit nicer like that. And then we will subtract the integral of dx. And the integral of dx is just x, and so this is equal to x times the natural log of x minus x plus c. Okay, and so that is the integral of the natural log of x by using integration by parts. So here's our next example. We have the integral of x squared times cosine x dx. And so what we want to do here is determine what we're going to set equal to u and what we're going to set equal to dv. Now in this case, our options are x squared and cosine x. And so for me, I like to determine which of those two functions is going to get simpler when I take the derivative of it. In this case, if you take the derivative of x squared, it becomes 2x, but the derivative of cosine is just negative sine, so it's not really getting any simpler. So I'm going to want to set u equal to x squared. Now if you like to use the acronym and you're following LIATE, then you know that x squared is an algebraic function, and that is higher in the list than trig functions, and so you know to set x squared equal to u. All right, and so let's do that. U will be equal to x squared, which means that dv will be equal to cosine x times dx. All right, so that is what we're going to set equal to u and dv. So let's take the derivative of u. We will have du dx is equal to 2x. That's using the power rule for derivatives. Multiply the exponent down and subtract 1 from the exponent. So we have 2x. And then if we solve for du, we'll have du is equal to 2x dx. Okay, now let's integrate dv. So the integral of dv is equal to the integral of cosine x dx. And the integral of cosine x is positive sine x. And so v is equal to sine x. Okay, and so let's rewrite this integral using our integration by parts formula. This will be equal to u times v. So we'll have x squared times sine x. So I'll write that, x squared times sine x. And then we will subtract the integral of v, which is still sine x, times du, which is 2x dx. So we will have 2x dx. All right, and so if I simplify and rewrite this a little bit, we'll have that this is equal to x squared times sine x. And then I'm going to pull this 2 to the outside. And so we'll have negative 2 times the integral of x times sine x times dx. So we have x times sine x times dx. And look what we have right here. We have another integral that we can't integrate unless we use integration by parts, right? This is actually one of the integrals that we solved earlier in this video. We have x times sine x dx, which we cannot solve with any other method other than integration by parts, and so we actually have to use integration by parts twice to solve this integral. And this is going to be something that is pretty common in a lot of integrals that you will solve with integration by parts. You will probably have to use the technique more than once in order to solve some integrals. And so because of that, we're going to have to pick a new u and pick a new dv. And so we're going to continue to set u equal to our algebraic function and set dv equal to sin x dx, our trig function. But to avoid confusion, I'm going to add subscripts to u and v so that we don't mix up our first batch of u and dv with our second batch that we're going to do now. So I'm going to add subscripts. This is u sub 1, du sub 1, and du sub 1. And then we'll have dv sub 1, dv sub 1, and v sub 1. All right, it's not a huge deal if you don't do this, but for the sake of this video, I want to make sure you understand what I'm using, and so I'm adding these subscripts to avoid any potential confusion. Okay, but what we're going to have here is that u2 is equal to x, that is this function right here, and dv sub 2 will be equal to sine x dx. So we'll have sine x dx. All right, and so if we take the derivative of u, we'll have du sub 2 divided by dx is equal to 1, because the derivative of x is 1, which means that du sub 2 is equal to dx. All right, and then if we integrate dv sub 2 and sin x dx, we'll have the integral of dv sub 2 is equal to the integral of sin x dx. And the integral of sin x dx is going to be negative cosine x. And so we'll have v sub 2 is equal to negative cosine x. All right, and so now let's rewrite this integral using our integration by parts formula. And I'm going to have to write a little bit smaller here, but this is equal to x squared times sine x minus 2. And then I'm going to write parentheses here so that we remember to distribute this negative 2 through both of the terms that are going to result from rewriting this integral. So we're going to have u2 times v2. So we're going to have x times negative cosine x. So we have x times negative cosine x. And then we will subtract the integral of v2 times du2. So we'll have negative cosine x times dx. And so I'll write that, negative cosine x times dx. All right, and so now we have an integral that is easier to solve. We know what the integral is of cosine x, and so now we can finally solve this integral after using integration by parts 2 times. All right, and so I'm going to clean up my work here now. I'm going to remove all of this so I have room to simplify this answer. All right, and so now let's simplify. This is equal to x squared times sine x minus 2 times negative x times cosine x, and then this negative for cosine and this negative will cancel out, so we'll have plus the integral of cosine x times dx. And if we distribute negative 2 to each part of this quantity, we'll have that this is equal to x squared times sine x plus 2x times cosine x minus 2 times the integral of cosine x dx. And then we know that the integral of cosine x is just sine x, And so I'll just rewrite that to be sine x, and then we'll add c. And so that is the solution to our integral that we started with. All right, so just be aware that sometimes you may need to use integration by parts more than once. So here's our next example. We have the integral of e to the power of x times sine x times dx. And so the first thing we want to do here, since we have a product of two functions that we can't integrate otherwise, is determine what we're going to set equal to u and what we're going to set equal to dv so that we can use integration by parts. Now in this case, if you were following the trick that I showed you earlier, and I think I made a note of this, that at the bottom of that list, you have trig functions and exponential functions, but they are interchangeable. And so if you're using that trick, in this case, you could choose u to be either of these functions, and integration by parts would work just fine. All right, and so it actually comes down to preference what you want to set equal to u and what you want to set equal to dv. Because if you look at both of these functions, if you take the derivative of e to the power of x, you just get e to the power of x back, and if you take the derivative of sine x, you get cosine x. So neither of those functions gets simpler when you take their derivative, and so you just kind of have to pick one to be u and then go with it. And so in this case, since I like to integrate exponential functions more than I like to integrate trig functions, I'm personally going to set u equal to sine so that dv is e to the power of x dx, and we can integrate e to the power of x. So I'm going to set sine x equal to u and e to the power of x dx equal to dv. So I'll have u is equal to sine x and dv is equal to e to the power of x dx. All right, and so the derivative du dx will be equal to cosine x, which means that du is equal to cosine x times dx. Then if we integrate dv, we'll have the integral of dv is equal to the integral of e to the power of x dx, and the integral of e to the power of x is just itself, so v is equal to e to the power of x. All right, and so let's rewrite this integral. Let's see what happens when we do that. We will have that this integral is equal to u times v, so we'll have sine x times e to the power of x. So I'll write sine x times e to the power of x, and then we will subtract the integral of v, which is e to the power of x, times du, which is cosine x dx. So I'll rewrite that. We'll have cosine x dx, and now we have an integral that is very similar to what we started with. Instead of having e to the power of x times sine x, we have e to the power of x times cosine x. And so we seemingly didn't really do anything. We just wrote another integral that we now need to use integration by parts for again. And so while it might seem like we're working towards a dead end, because it looks like this is never going to end if we keep using integration by parts, watch what happens if we use integration by parts just one more time. Doing it a second time is going to reveal something pretty cool about this integral. And so let's do that. We're going to have to choose a new u and a new dv. And so I'm going to use subscripts again so that you don't get confused with what we're setting equal to u and what is going to be dv. But first, let me just rewrite this. This will be equal to e to the power of x times sine x minus the integral of e to the power of x cosine x dx. All right, that way we don't have the previous colors interfering with our new u and our new dv. Okay, so let's pick a new u and a new dv. I'm going to do the same thing I did last time. I'm going to set u equal to the trig function and set dv equal to e to the power of x dx. And before I write that down, I just want to add subscripts to u and v over here. So we'll have u sub 1 over here, and then v sub 1 as well. All right, and so now let's work with our new u and our new dv. So we'll have u sub 2 is equal to cosine x, and we will have dv sub 2 is equal to e to the power of x dx. And so du sub 2 divided by dx will be equal to the derivative of cosine, which is negative sine x. And so that means that du sub 2 is equal to negative sine x times dx. All right, and then let's integrate dv. So we'll have the integral of dv sub 2 is equal to the integral of e to the power of x dx. And once again, the integral of e to the power of x is just itself, and so v sub 2 is equal to e to the power of x. All right, and so if we rewrite this integral using the information that we just found, we will have that this is equal to e to the power of x times sine x minus both of those new terms. And I'm going to put them in parentheses so that this negative is distributed to both of these new terms that comes from rewriting this integral with integration by parts. So we're going to have u times v, which will be cosine x times e to the power of x. And so we'll have cosine x times e to the power of x. And then we will subtract the integral of v, which is e to the power of x times du. And that is negative sine x times dx. Okay, and so if we simplify, this is equal to e to the power of x times sine x, and we will subtract e to the power of x times cosine x, and then we can pull this negative out front, and it will become positive because a negative times a negative is positive. So we'll have plus the integral of e to the power of x times sine x dx. And then don't forget to close that because we need to distribute this negative to both terms yet. And so if I clean up my work here, let's distribute that negative. We'll have that this is equal to e to the power of x times sine x minus e to the power of x times cosine x. And then that negative will make this integral negative, so we'll have minus the integral of e to the power of x times sine x dx. And now it seems like at this point, like I said earlier, that we've reached a dead end, right? We have another integral that it seems like we're going to need to use integration by parts for again. However, notice that this integral is the exact same integral that we started with, right? We're trying to solve the integral of e to the power of x times sine x dx, and we now have that integral within the solution to that integral. And so this is where something really cool comes into play. Remember that we were saying that this integral is equal to this expression. So if I write that in there, let's write that the integral of e to the power of x times sine x dx is equal to this expression. Now what we can do is combine like terms. We have two integrals that are like integrals. We can add this integral to both sides of the equation, and we will have two of those integrals on this side of the equation, right? So if we add this integral to both sides, that will cancel out with this negative integral, and we will have 2 times the integral of e to the power of x times sine x dx is equal to e to the power of x times sine x minus e to the power of x times cosine x. And now what that allows us to do is divide both sides by 2, right? So if we do that, this 2 will cancel out, and then both of these terms will be divided by 2, and now we have that the integral of e to the power of x times sine x dx, which is what we started with, that's what we want to solve, is equal to this expression. All we're missing is a plus c. And now this is the solution to this integral. All right, so what we learn here is that when you're working with integration by parts, and you notice that the integral that you're writing isn't getting any simpler, try using integration by parts again and see if you get an integral that is the same as the integral you were trying to solve. Because then all you have to do is combine them, and then you can solve for your solution. All right, and so let's look at one more example for this video. I just want to show you how you would use integration by parts if you have a definite integral. All right, so here's our last example. We have a much simpler integral to solve by using integration by parts. What I want to demonstrate here is how you would handle a definite integral when you need to use integration by parts, because it can be a little confusing if you've never seen it before. All right, so in this case, we have x times cosine x. And so if you're following the acronym, you know you want to choose the algebraic part to be u over the trig part. But for me, I know that x is going to get simpler when I take its derivative, so I'm going to set u equal to x. All right, so u is equal to x, which means that dv will be equal to cosine x times dx. All right, and so du dx, the derivative of u, will be equal to 1, since the derivative of x is 1, which means that du is equal to dx. All right, and then the integral of dv will be equal to the integral of cosine x dx, and the integral of cosine x is sine x, and so we have v is equal to sine x. All right, and so then this is where it differs just a little bit when you have a definite integral. When you rewrite this integral with these two terms over here, you're going to be evaluating both of them for your bounds. So what we're going to have is that this is equal to the evaluation of u times v. So we'll have x times sine x minus the integral of v, which is sine x, times du, which is dx. And then we'll close that, and the evaluation is from 0 to pi. All right, so then we'll solve this integral, and then we'll plug our bounds into everything inside these brackets. And so if we rewrite this and integrate sine x, we know that the integral of sine x is negative cosine x, and so this is equal to x times sine x minus negative cosine x evaluated from 0 to pi. All right, and so that will be equal to x times sine x plus cosine x evaluated from 0 to pi. And so if I clean up my work here, we can evaluate this expression at pi and then subtract the evaluation at 0, and we'll have that this is equal to pi times sine of pi plus cosine of pi minus 0 times sine of 0 plus cosine of 0. All right, so this will be equal to pi times sine of pi, which is equal to 0. So we have pi times 0 plus cosine of pi, which is negative 1. So we'll add negative 1, and then we will subtract 0 times sine of 0. Anything times 0 is 0. And so that's just going to be 0. And then plus cosine of 0, which is positive 1. So we'll have 1. And so pi times 0 is just 0. And so this is equal to negative 1 minus 0 plus 1, which is just positive 1. So we have negative 1 minus 1, which will be equal to negative 2. And so negative 2 is the solution to this definite integral. Okay, and so that's all I had for this video on integration by parts. If you want to see some more examples, feel free to check out my examples video that I'll have linked at the end of this video, as well as in the description below. If you have any questions, feel free to leave those in the comments, but if you don't have any questions, this is all I had for now, so I will see you next time.